In numerical linear algebra, the Gauss-Seidel method, also known as the Liebmann method or the method of successive displacement, is an iterative method used to solve a linear system of equations. It is named after the German mathematicians Carl Friedrich Gauss and Philipp Ludwig von Seidel, and is similar to the Jacobi method, though it can be applied to any matrix with non-zero elements on the diagonals. Convergence is only guaranteed if the matrix is either diagonally dominant, or symmetric and positive definite. It was only mentioned in a private letter from Gauss to his student Girling in 1823. A publication was not delivered before 1874 by Seidel. Description: the Gauss-Seidel method is an iterative technique for solving a square system of n linear equations with unknown x. It is defined by the iteration where is the kth approximation or iteration of is the next or k+1 iteration of, and the matrix A is decomposed into a lower triangular component, and a strictly upper triangular component U. In more detail, write out A, x and B in the components. Then the decomposition of A into its lower triangular component and its strictly upper triangular component is given by. The system of linear equations may be rewritten as. The Gauss-Seidel method now solves the left-hand side of this expression for x, using previous value for ex on the right-hand side. Analytically, this may be written as. However, by taking advantage of the triangular form of, the elements of x can be computed sequentially using forward substitution. The procedure is generally continued until the changes made by an iteration are below some tolerance, such as a sufficiently small residual. Discussion: the element-wise formula for the Gauss-Seidel method is extremely similar to that of the Jacobi method. The computation of xi uses only the elements of x that have already been computed, and only the elements of x that have not yet to be advanced to iteration k+1. This means that, unlike the Jacobi method, only one storage vector is required as elements can be overwritten as they're computed, which can be advantageous for very large problems. However, unlike the Jacobi method, the computations for each element cannot be done in parallel. Furthermore, the values at each iteration are dependent on the order of the original equations. Gauss-Seidel is the same I saw with convergence. The convergence properties of the Gauss-Seidel method are dependent on the matrix A, namely, the procedure is known to converge if either A is symmetric positive definite, or A is strictly or irreducibly diagonally dominant. The Gauss-Seidel method sometimes converges even if these conditions are not satisfied. Algorithm: since elements can be overwritten as they are computed in this algorithm, only one storage vector is needed, and vector indexing is omitted. The algorithm goes as follows. Inputs: A, B. Output: choose an initial guess to the solution. Repeat until convergence for I from 1 until n. Do for j from 1 until n. Do if j I then end if end, and check if convergence is reached. End examples. An example for the matrix version: a linear system shown as is given by, and we want to use the equation in the form where, and we must decompose into the sum of a lower triangular component and a strict upper triangular component, and the inverse of is. Now we can find. Now we have and we can use them to obtain the vectors iteratively. First of all, we have to choose. We can only guess. The better the guess, the quicker the algorithm will perform. We suppose. We can then calculate. As expected, the algorithm converges to the exact solution. In fact, the matrix A is strictly diagonally dominant. Another example for the matrix version: another linear system shown as is given by, and we want to use the equation in the form where, and we must decompose into the sum of a lower triangular component and a strict upper triangular component, and the inverse of is. Now we can find. Now we have and we can use them to obtain the vectors iteratively. First of all, we have to choose. We can only guess. The better the guess, the quicker will perform the algorithm. We suppose. We can then calculate. If we test for convergence, we'll find that the algorithm diverges. In fact, the matrix A is neither diagonally dominant nor positive definite. Then, convergence to the exact solution is not guaranteed and, in this case, will not occur. An example for the equation version: suppose given k equations where xn are vectors of these equations and starting point x0. From the first equation, solve for ex1 in terms of for the next equations, substitute the previous values of xs. To make it clear, let's consider an example. Solving for, and gives. Suppose we choose as the initial approximation, then the first approximate solution is given by using the approximations obtained. The iterative procedure is repeated until the desired accuracy has been reached. The following are the approximated solutions after 4 iterations. The exact solution of the system is. An example using Python 3 and NumPy. The following numerical procedure simply iterates to produce the solution vector. Import NumPy as np iteration underscore limit equals 1000 hash initialize the matrix A equals np dot array hash initialize the RHS vector B equals np dot array hash prints the system print for I in range. Row equals asterisk x, format for j in range, print equals b, I, print for it underscore count in range, print x underscore new equals np, zeros underscore like for I in range, s1 equals np dot dot s2 equals np dot dot x underscore new, I equals a, I, if np dot all close. Break x equals x underscore new print error equals np dot dot b print produces the output. System 10.0 asterisk x1 plus minus 1.0 asterisk x2 plus 2.0 asterisk x3 plus 0.0 asterisk x4 equals 6.0 minus 1.0 asterisk x1 plus 11.0 asterisk x2 plus minus 1.0 asterisk x3 plus 3.0 asterisk x4 equals 25.0 2.0 asterisk x1 plus minus 1.0 asterisk x2 plus 10.0 asterisk x3 plus minus 1.0 asterisk x4 equals minus 11.0 0.0 asterisk x1 plus 3.0 asterisk x2 plus minus 1.0 asterisk x3 plus 8.0 asterisk x4 equals 15.0 current solution 0, 0, 0, 0 current solution 0.62.327272773 minus 0.987272730 0.878866364 current solution 1.030181822.0369380 minus 1.0144562 0.984344122 current solution 1.006585042.0035550 minus 1.002527380 0.998355095 current solution 1.0086098 minus 1.000307280 0.9998495 current solution 1.000912822.0002134 minus 1.0003115 0.9999881 current solution 1.0008362.0000117 minus 1.0000275 0.9999922 current solution 1.0000672.0000002 minus 1.0000021 0.9999996 current solution 1.00004 minus 1.0000011 current solution 1 2, minus 1, 1, solution, 1, 2, minus 1, 1, error, 2.0648093 minus 1.2555105 3.6141756 times 10 to the minus 11 0.00000000 E plus 00. Program to solve arbitrary no.